Welcome everybody to Lecture 6 of Submodular Functions Optimization and Applications to Machine Learning. And today we will be doing a couple of new things and also reviewing a couple of old things, as usual. I've assigned a new bit of reading today, so you should be reading both sections or chapters 1 and 2 from Fujishiki's book, and also sections 3.1 through 3.2. It's a little bit more reading to do. And also, at long last, we have a homework assignment, which is due, namely homework 1. And it's due next Wednesday, so 1 week from today at 11:45 p.m. And you need to do it electronically. So, obviously, I'm not going to be here in this classroom at 11:45 p.m., but you need to turn it in electronically by then. And you can do so at the following link, where you can upload your assignment in PDF format. So it has to be PDF format. So you could do it electronically if you want, using something like LaTeX, or if you like, you can just do it on paper and then take high resolution and very, very easy to read photos of your papers, convert them to a PDF file and upload that. So that's perfectly fine. So however you want to convert your PDF, you want to do it on paper, do it the traditional way or not, it has to be a PDF file and uploaded. They'll be graded electronically, and they'll be graded as hopefully soon after they're uploaded. Rishabh, our TA, will be doing the grading, and they will be graded right there and then, so you'll actually be able to go, as soon as it's done being graded, and look up the markups on the Canvas webpage. So that's pretty neat, I think. I'm still kind of happy about that. So today we're going to be doing this more on Matroids. And we're going to be seeing a couple of different interesting examples of them, namely the system, transversals, which is something that we'll be spending a bit of time on understanding. And as I mentioned last time, I think they're interesting to study because they're a very interesting class of matroids. We'll be talking about matroids and representation and getting a little bit into that and some of the topics that actually occur today or occur in matroid theory, which is, for example, trying to look at isomorphisms between matroids. And then lastly, look at a dual matroid. And a dual matroid is an amazing construct because it produces matroids that, if you look at what the independent sets are, they're completely different than what you would expect based on our intuition about a graph. And I think that's kind of fun because you'll see that independent sets are totally different than what you think of as independent in a graphic matroid. But we'll be using a graph to study that. So let's just do a little bit of review. So we have a set system, again, and it's a matroid if we have these three properties. It has to be empty set containing, it has to be down closed, and it has to have essentially this exchange-like property, namely that if you have a smaller and a larger independent set, then there has to be an element in the larger that's not in the smaller one that can be added to the smaller one, and you retain independence. Okay, it's a matroid. We saw that matroids are such that all maximally independent sets have the same size. So if you have any arbitrary set, say x, oops, not there, but here. If you have any arbitrary set x, then all bases of x have the same size. And because of that, it's valid to talk about the rank function. So, namely either the rank of a matroid or the rank of a set. And the rank of a set is basically the size of the maximally independent set contained within the set X. And there's two ways of writing it. We can write it in this fashion, or we can just write it as the max over a bunch of modular functions. And we have these number of properties, namely like the rank is never greater than the cardinality, and so on and so forth, that we saw last time. We saw a very important property about rank functions, namely that rank functions are submodular. And as I will, I think, begin to argue, especially when we look at some of these instances of matroids, you'll see that already the rank function gives us an incredibly diverse class of submodular functions, even though, as we saw last time, the rank function has certain restrictions, namely that it basically is an all or nothing proposition. Namely, if you add an element, first of all, it's integral valued. Right? So you don't get real values, you only get integers, number one, in a rank function of a matroid. Number two, when you add a new item, either you increase the rank by 1 or you increase the rank by 0. So, like in the matrix case, every time you add a new element, either you're completely spanning a new subspace, or you're not. Okay, and if you do span a new space, the rank goes up by 1, or otherwise it's not. And that's something that's true of all matroids. That basically, when you add an element, either you're completely seeing something brand new that you've never even partially seen before, or it's entirely redundant. So, but on the other hand, you get some very interesting structural properties, which we'll see today. So we defined last time also the partition matroid, and what a partition matroid was one where we take the ground set and we partition into some number of blocks, V1 through VL, which are disjoint subsets, and we cover. And we define a set of independent sets so that you can't be, if you're independent, as long as you don't intersect any of the block more than some block budget, which is given by K sub I. Okay. We also saw the rank function of a partition matroid has this following form. By the way, you should guys, I always leave this mouse in the middle of the screen. If you see this mouse pointer there, then remind me to remove it, because it's not something I can remove after the fact. So if that thing shouldn't be there, so please remind me. Anyway, getting back to the topic at hand, we have the rank function of a partition matroid, which is very intuitive because it basically never gives you any additional valuation by having an intersection within any of the blocks more than, say, K. So as long you get value in the rank as long as you go up to size K, but as soon as you hit size K or Ki in this particular case for a particular block I, you never get increased value. And so therefore this is submodular. Now we know this is submodular also, we saw from the properties of submodular we saw before, but we also know this is submodular because this is the rank function of our partition matrix. And we also saw that a partition matrix corresponds to a matching, independent sets correspond to matching in a particular type of bipartite graph. So we have a bipartite graph where we have nodes on the left and the right, and basically we induce, we saw this last time in yellow, we choose a particular set X, namely, let's choose a particular set of items, and then the matching would be one where we match maybe each of these vertices on the left that we've chosen, and that basically is an independent set. So the independent set is the rank. And the K, again, this is important to realize in case this is not clear. So Ki, which is like the block limit within a particular block of a partition matroid, corresponds to the number of nodes on the grouping on the right-hand side. Now, one thing you should note is that this is really a partition of the bipartite graph is not connected. It consists of multiple connected components. Namely, we have this connected component, and this connected component, and this one, and this one, and this one. Right? So we have multiple connected components. There's no edge, say, that goes from here to here. Right? And that particular bipartite graph corresponds to a partition matroid and gives us, via matchings, the partition matroid rank function. Okay. And bases, what are bases? Well, a base of a particular set is a maximum matching, and then a base of a matroid is the maximum matching in the bipartite graph. So all maximum matchings in this bipartite graph correspond to bases of the matroid. And all maximum matchings, therefore, are the same size in this bipartite graph. So any questions about that? Okay, so we're going to generalize this using a number of different concepts. So we're going to first of all define a system of representatives. So first of all, we're starting with the set system. Are you sure there are no questions? Because we will now lead to more things that are more confusing. If you're confused about what we've been talking about, this is the time to ask, not 3 slides from now. If you have any questions, comments, clarifications. Okay, so system of representatives. We start with the set system, and so script V is basically going to be a set of subsets of V. So these are subsets of V. And then I is always going to be the index set, right? So I is our index set. We have essentially cardinality of I subsets. And that's expressed by this guy, by this guy right here. Okay. And what we're going to think of these are groups. Okay. So this is not necessarily a partition like we saw before. So in other words, VI and VJ could potentially intersect. And these could be potentially thought of as groups, like you might think of them as interest groups of individuals. Like let's say that V is a group of people. This V here is a group of people. And let's say that, you might be in one of a number of groups, like maybe you're in a group of people who are in this class, right? But you're taking other classes, and some subset of you might be in this class in the convex optimization class. And so you might be, or you might have different interest groups. Like some people might be interested in sailing, and other people might be interested in cooking, and other people might be interested in skiing. And there might be some intersection between these groups. Okay, the groups need not be disjoint. So you can think of them as interest groups. Now, a system of representatives is basically a family, namely a set of guys, and you have, one for each element in I. So V of I is lowercase v of I is a member of V. And it's a system of representatives if essentially every group has a representative. So it's just what it basically represents. For each group, you choose a representative. And so you have as many representatives as you have groups. And the idea being is that it's sort of a representative. Like if you want to have a meeting amongst all of the groups, you don't want all of the groups to come to the meeting, but you at least want to have each group have a representative at the meeting. And so a system of representatives would be essentially, in some sense, the minimal set of individuals that ensures that each group has a representative at the meeting. And you can look at it mathematically by saying that there's a bijection, pi. It's a bijection from I to I, which basically ensures that V sub I is a member of the pi ith group. Okay. So now, why does that ensure? Why does that ensure that every group is represented? Because it's a bijection. Bijection basically means it's one-to-one and onto. So that basically means that it's sort of like, you can think of it as a permutation, right? So it's basically every element of I exists both in the range and the domain of this mapping. And so therefore every group is represented. Every group has a particular individual who's its representative. And again, like I've said, VI is the representative of group pi I. I keep saying this many, many times over and over again. So the ith representative is meant to represent V sub pi I. Okay? Should I say it again? No. I'm going to say it again. Here's another example. Like the House of Representatives is an example, in some sense, because we have our representative here is Jim McDermott, and he represents District 7, the Washington District 7, which is King County. But on the other hand, this doesn't really get at the nature. The House of Representatives is really sort of a partitioning of the districts. What we're not saying necessarily is that it's a partition because we can have different interest groups. You could be a member of the sailing group and the cooking group. So that's not a particularly good example. Now, in a particular system of representatives, there's no requirement for the representatives to be distinct. So in this meeting, let's say that all the representatives go to the meeting. If you could be a member of the sailing group and the cooking group, and if you went, you would be a representative of both groups. So in other words, that would be saying that, for example, you could have the representative being a member of group 1 and group 2. Right? Now, that doesn't, so in other words, these guys could be, VI could be equal to VJ. So that the representatives are not distinct. Okay? And that's the difference between what we're going to call a system of representatives and a system of distinct representatives, which we will see shortly. Yes, question?
Okay, so I have a confusion. I got confused. And this is that, why do you need a pi? Well, what's wrong in saying smaller vi belongs to capital Vi? Or is there something subtle going on?
Well, because we're not imposing a particular specifically prescribed order on the VIs such that there needs to be an alignment between VI and V pi I. I mean, it might be the case that we just chose to name the VIs with the subscript I, and we're not saying that the I has to be the same as the ith group. Like you're the ith person, the ith representative might represent the jth group for some other group. As long as there's a crossing. We'll see. Let's take a look at this bipartite graph example, and maybe that will answer this question a little bit better. But let's look at it as a bipartite graph. So on the left-hand side here, we have the individuals, maybe the members or the people. And let's zoom in a little bit. And each person has essentially a set of labels or colors. And each person has a color that, and the colors next to the person corresponds to the groups that person is in. So person A is in the green group, the magenta group, the green group, the magenta group, or whatever that color is, and the red group. What color is that? Does anyone know? Is that magenta? I see different colors than you see, but I hope hopefully it looks somewhat semi-magenta. And person B is in the green group and the blue group, person C is in the blue group, person D is in the red group. Now the bipartite graph is sort of representing this information redundantly because on the right-hand side we have essentially the list of groups. Right? Here's a list of groups. And so A is a member of the red group, the purple group, and the green group. Right? So the bipartite graph also represents the grouping, as does the colors. So we have, how many groups do we have? We have 6 groups. These are the groups, and these are the groupings, right? So V1, which is EFH. So that's basically E, F, and H here, which is this. V2 is DEG, and so on and so forth, right? DEG. Okay, so everybody should be clear on that. Now, what a system of representatives does is it's basically a subset of V such that every one of the groups on the right is represented. So that basically means if we take the union of colors of the representatives on the left, it has to equal the union of colors on the right, and that's how it works. And here's, for example, a particular representative. So the representatives come in this case are A, C, D, F, and H. So A represents the red group and the purple group. C represents the blue group. D represents the red group. F represents the yellow group, and H represents the green group. So that's a system of representatives. Notice that A represents both the red group and the purple group. And so is this set of representatives distinct? No, because 2 groups, namely the red group and the purple group, have the same representative. So it's not distinct. Well, we already answered that question. Now, in fact, is it possible in this particular bipartite graph to have a set of distinct representatives? Why?
Group 5 and 6, the only member is A.
That's right. Group 5 and 6, the only member is A, and there's impossible. There's no way to represent both groups because the only member of those groups is A. So A is a member of maybe the red group is let's call it Seattle Coconut Tree Growers Association. Okay, there aren't that many people in Seattle who are members of the Seattle Coconut Tree Growers Association, and A is a member of that group, and A is also a member of say the Jamaican Snow Skiers Association. Right, there are very few members of the Jamaican Snow Skiers Association, but A is for some reason a member of both, and also A is a member of maybe Northwest Coffee. It's this popular group like Green. So there's no way to have a system of distinct representatives. There's only one common choice to represent both groups. Okay, so now let's talk about a system of distinct representatives. Again, we have a set system. Okay, and so we have a set of sets, and each one of them are subsets, and it's an index. So basically nothing has changed yet. The only thing that's changed, so it's a system of distinct representatives if it's the case that each group has as its representative a person who's unique. So that means that if you go to this meeting and all of the groups have a representative, you can't have anybody representing more than one group. Okay? You can't have you don't want to have anybody representing 0 groups either. But you have nobody representing more than one group, and so that means that each group is represented and it's distinct. And so you can think of it as a bijection, and the bijection ensures that all groups are represented. But then also you impose this condition, that namely that Vi and Vj are unequal, and so it's distinct. So a system of distinct representatives has this as a requirement. And this is a system of annoying bells. So it seems like the randomness of the time that the bell happens is what makes it most annoying. Or at least I don't keep track of precisely what's happening. So let's restate this again. So a system of distinct representatives is often called a transversal. And so we're going to define a transversal. We're just going to have a nice, clear and concise definition. A set system, as defined above, is a transversal if there's a bijection from T to I. So here in this particular case, T is the actual representatives themselves, not the index. And then I is the index set. And what this says is that for all members of T, this maps to group V sub pi of x. So x maps to group V of pi of x. Now, why is this guarantee that it's distinct? Like, why is this the same as a system of distinct representatives? Because notationally, we've only changed a little bit. So in other words, we're not here even saying this stuff up here. It's a bijection. We had a bijection here too.
That's from T to I instead of I.
It's because what?
The bijection I maps from T to I instead of I to I.
It's from T to I. And so it's from members. So it's a bijection and basically says that each member has to go to a particular group. And since it's a bijection, it's a one-to-one onto, it basically says it's the same sizes. The size of T is the same as the size of I. And so every member has a corresponding group and vice versa. Nobody gets reused. So that's answered down here. So you can say that maybe everything is in some sense covered. Okay, so this is the transversal. Now you might think, oh look, here you've got a set system. Are these things, does this thing have anything to do with the matroid? This is what we're going to answer. Because remember, a matroid is a set system. A set system isn't necessarily a matroid. But this seems like it may be a very interesting matroid. Let's see if we can get some understanding on it. But before we do so, let's introduce a little bit of notation. I mean, we have the subclusivity property, namely that if we have, you have this notion, so basically any set, so this is, make sure that this terminology is clear. Any set that has this property is called a transversal. So remember, a transversal is a subset of V, such that every member is a unique representative of some group.
Does that include the image and all groups have to be covered?
What do you think? So from notationally?
Yes.
Because of the right-hand side of this, yes. If you think yes, you're right. And the reason why is because it's one-to-one onto, it's bijection onto I.
It's just like a basic
We'll get to that. It's a very good intuition, if you're having that intuition. So I don't want to spill the beans, if that makes any sense. But anyway, let's first of all talk about a partial transversal. So we have, if a given set, a subset of V is a partial transversal if X is the transversal of some subfamily. So basically, if it's possible to choose a subset of the set of sets, which is namely script V prime, so I prime is a subset of I, and if it's a transversal of that, then it's called a partial transversal. And so we can see right away that if we take any transversal, then any subset of transversal is going to be a partial transversal. And why is that? Because we haven't lost the uniqueness. And all we're doing is like every time we remove a member, like let's say in this meeting we remove the sole member of this Northwestern Alliance for Coconut Tree Growers or something, whatever we called it before. If we remove that person and that group, all of the rest of the groups would have their single unique representative. Right? So, therefore, transversals are damn closed. Okay, so now what we want to do, before we actually get into the matroidality of this, we want to try to characterize when transversals exist and how to tell. So this is a really neat thing, and this is actually going to get into something that we're going to see is our first example of submodular function minimization. It's going to sort of come up on you very strangely. So we've got a set system, and also another very interesting property, another compositional property of submodular functions we're going to see. So we got a set system. Again, this is a set of subsets, and I is the index set, and just like what we saw. And this is to define this function v of j. So notice that I can be seen in some sense as a separate ground set. In a bipartite graph, we have the left vertices and the right vertices. The left vertices are like one ground set. The right vertices are like another ground set. The right vertices are like an index set. And we can actually define a mapping from subsets of right vertices to subsets of left vertices via this function, right? Everybody see that? And in fact, we saw that this is a submodular function. If we take the cardinality of v of j, we know this is a submodular function. Namely, v of j is seen as a function from 2 to the I to the non-negative integers, right? And that's submodular, which we saw before. So what we're going to get is Hall's theorem. So when we have, has anyone ever seen Hall's theorem before? Raise your hand if you've seen it. Okay, a couple. That's good. So this is a famous theorem in combinatorics. Basically, if we've got a set system and we have a family of subsets, then a transversal exists if and only if for all subsets of indices, the corresponding neighbors on the left of the set of indices is bigger than the set of indices. So if J is a set of indices, and the corresponding neighbors of the set of indices has to be no less than the set of indices. And in order to offer some intuition as to why this works, here's Hall's theorem again. Yep.
Is it not enough if it's true for the largest weight?
It has to be all subsets. It's not enough if it's true for the largest one. In other words, it's an if and only if condition. It has to be true for all subsets. Let's see if we can gain some intuition as to why that is the case here. What if it was the case that, for example, here's an answer to this question. On the left-hand side, let's say that the size of V is larger than the size of I, and there's one index on the right which is connected to everybody on the left. So right away it's satisfied for the largest index set, right? But it still could be the case. So in other words, here's a picture. So here's V, and here's I. I think this answers your question, I hope. And let's say that this is connected to everybody. This one guy over here is connected to everybody. Okay. But on the other hand, there's one group here, which has this kind of connection. There's two groups which have the same one. Okay, so if you take the whole set, it's going to be true, right? Because the number of nodes on the left is bigger than the number of nodes on the right. But if you take this particular guy, if you're trying to identify transversal, it can't be unique because the only possible person to represent this group, these two groups, this group and this group, is this guy. So transversal can't exist.
But it's a system of distinct representatives, right? So you cannot use every one of those on the
Sorry, I didn't understand the question, but what I'm saying is that every group has to have a representative who's distinct. And so this guy, each of these two, let's zoom in on this on the right a little bit so you can see.
That I understand, but you said that for the one on the top, you could use like every one on that side, but it has to be this, well, I see. So you can have more than one for every group then? Or it's not like a cover then?
Well, a cover can have more than one, but basically what it is it has to be the case that you can find a subset of these that are unique and that every group is covered. So it is like a covering. There could be more than one. There could be more than one transversal. But the critical thing is that you can't have just a system of representatives. The representatives needs to be distinct. And this particular picture that I just drew, you have this group here and this group here, which only have, these are these two groups, the Northwest Coconut People and the Jamaican Skiing Society, right? These are the two groups and they have only one member. And even though it's the case that if you look at the neighbors of this, it's bigger. So if this is J and this is V of J, that's the size of that's obviously going to be bigger than this. But on the other hand, if you look at this little subset here as J, and this is V of J, you're going to have this is smaller than that.
If you can have
Terrible picture, I know. But maybe color will disambiguate it a little bit.
But if you have an extra constraint that there can only be one for every group, then that should be.
Well, what we're trying to do is prove this theorem, or that's what we want to do. We want to say that this is an if and only if condition. So in other words, if this is true for all j, then it's true and vice versa. Yeah, Bethany?
And if it's confused about like the little v's have to be one per group, but the big v's that we're using are all of the numbers, not one number.
Yeah, no, I understand. I'm just saying that, if you could then add an extra constraint that we can only have one for every group, then in that case that would fail because for that group it's not going to be the same. You're going to have one that's bigger than the right side.
I think that you're right if that's a constraint that defines the thing, but what we want to do is identify a characterization, an if and only if condition that characterizes a transversal. So you're right in the sense that you're coming up with a description that characterizes it. In fact, if we took a system of representatives, remember this guy? Where we added this one? I think that's what you're saying.
No, I'm saying if you want that and you want to say that there can only be one member on the left side that matches onto any one on the right side. So if one on the right side is taken, then you cannot add anything more on the right side that's going to have on the same. In which case, if there's something that's not be two here, it's not going to be this thing. Then it's going to be
Yeah, but that is again restating this. What I'm claiming is that what you're saying is restating exactly what the definition of the system distinct representatives are. And what we want to do is we want to show that, like I said, we want to show that this theorem is true. But before we show that this theorem is true, I just want to make sure that this intuition is clear. So like for example, here's an example where V and I, this is a slightly different example, and here would be an example of a system of distinct representatives. All right. Now, is it the case that Hall's theorem is satisfied for this particular bipartite graph? I mean, right away you can sort of see it because when you look at the neighbors of all the right-hand side guys, that each of these right-hand side vertices have degree 3, I think, or 3 or more. And we have more nodes on the left than on the right. But I mean, it's a little bit trickier than that to do that because you need this thing. And this is a combinatorial condition, right? So to check this, you might say, oh great, this is a great theorem. Now all I need to do if I've got a particular massive bipartite graph, is check all exponentially large number of subsets of J. Let's say I've got 50 groups, then it would be 2 to the 50 things I would need to check to see whether or not each of the 50 groups could have a unique person representing it. Do you think there's a faster algorithm for this? Okay, we will see. Let's generalize this theorem and, from Hall's theorem to Radu's theorem. Now, let's say that you have some matroid. Okay, this is a completely separate matroid. This is actually you'll like this, I think. You have a matroid M, and the matroid has nothing to do with the transversal, right? It's just some matroid, and you have a rank function R, which we know now defines a matroid. And we have this family of subsets, right? Right? So in other words, the matroid has nothing to do with the set system. We have the matroid and the set system associated with the matroid, but right now what we're doing is defining the matroid with respect to R, and we've got the transversal, which is another set system, which we haven't said anything associated yet with the matroid. And what we're saying is that this set system, the set system that might or might not have a transversal, it has a transversal that's independent in the matroid, if and only if for all subsets, the rank of the left neighbors is greater than or equal to the cardinality of the index set. So you've got some index set J, and the rank of the neighbors of the index set J has to be no less than the size of the index set. Okay. So if we take the free matroid, we immediately get Hall's theorem, right? Because basically everything's independent. So here we're qualifying it. We're saying it's a transversal on the one hand, and also that's independent in the matroid. But so obviously, if we take the rank is equal to the cardinality, which gives us the free matroid, then that gives us back Hall's theorem. Does everybody see that? Okay. But we're going to generalize this a little bit even further to the polymatroidal transversal theorem. And what this says is that we've got some set system, V, finite family of non-empty subsets of V, and we've got some polymatroid function. It's an integral polymatroid function. Integral, which means it's non-negative, integral, monotone, non-decreasing, and submodular. Okay. So then, what the theorem states is this set system has a system of representatives such that this is true if and only if this is true. Okay.
Is this distinct system of representatives, or
We're saying it's a system of representatives.
so not necessarily distinct?
I'm not necessarily saying it's distinct. But we could make it distinct. How would we make it distinct? So f is any integral value polymatroid function. What if we take f is equal to the cardinality? Does that would make it distinct, right? Because then we'd recover Hall's theorem. But in other words, here's another way of saying it. So it's a system of representatives with this property. With the property that I just circled. And that property is based on whatever that polymatroid function happens to be. We can make it distinct by setting it equal to the cardinality function, which is an integral value polymatroid function. We can make it distinct and independent in a matroid if we make the polymatroid function a matroid function. Or we can just make it whatever we want, just by essentially saying that that polymatroid function can be some other polymatroid function. Is that clear? The statement of the theorem? What we're going to do is we're going to prove this most general version of the theorem. So given theorem 6.4.3, we immediately get 6.4.1 by taking the cardinality function, in which case we do require the system of representatives to be distinct. Okay. And we get theorem 6.4.2, which is Ryder's theorem, by taking Polymatroid function to be a matroid Lang function, in which it says that systems of representatives is independent of M. So remember, in the right. So we get we get these two theorems by this one theorem. So what we're going to do now is prove this theorem. Are there any questions on what this theorem states? Okay, so one thing before I want to do that is let's look at this particular condition. So the basic condition is this inequality. It's basically saying that f of the neighbors of the indices has to be greater than or equal to the cardinality of the indices. And where f is a non-negative integral monotone of non-decreasing and submodular function, and where v is equal to this sort of set neighbor mapping functions, right? So this function can be seen. I don't know if I have this in the next slide. Let me see. When you look at this function here, so v of j is really a function that maps from 2 to the I to 2 to the V. Right. It's a function that maps from subsets of I to subsets of V. And so it's therefore reasonable to sort of use as something to compose within a submodular functions. Like in concave, when you have concave and convex functions, you can actually compose convex and concave functions as long as the dimensionality of the input and the output match. Like if you have a concave function whose output is an n-dimensional space, you can take that as the input of a convex function whose input is n-dimensional. You can't do that. You can't take the submodular function of a concave function because it's just the wrong type. But here, what one can do is, for example, define a new function, f g of j, and that defines a function on 2 to the I and maps to integers, right? Not necessarily non-negative anymore because we're subtracting off the cardinality, so we don't know if that's non-negative. But what it says is that the condition for the existence of a system of representatives with quality 6.5 becomes whether or not the minimization of this particular function g is non-negative. Now, what kind of problem is equation 6.7? It turns out that, does anyone have a guess as to what kind of function g is? I'll give you a hint. It has something to do with the title of this course. It's an optimization function. No, it's a machine learning function. No, it's a function. No, there's only one word left. It's a comma function. No, it's a submodular function. It is a submodular function. So in fact, it's not so hard to prove, and I'll probably put this on your next homework. It's very easy to prove, in fact. I only put easy problems on your homework. So the condition for existence of a transversal in the particular case, or these more general problems, whether or not there's a system of representatives with this particular property, is determined by the submodular function minimization problem. So basically, this is now, it's kind of interesting because people were studying this back in the 60s, back before even there was really even a clear sort of universal notion of submodular function, before Jack Edmonds' famous paper. And people were, in operations research, building on these sort of constructs, trying to do useful things, I think, like pack truck boxes into trucks. That was what people cared about in the 1960s, was packing boxes in trucks. These days, what we're interested in doing is finding how many Facebook friends you have and sending advertisements to you optimally. We've really advanced as a civilization from packing boxes into trucks to sending good junk mail. But regardless of the applications of what we're trying to do, it was interesting that basically people were thinking about these kinds of problems and saying, well, look at this particular optimization problem. If I were to try to solve this, it would be really bad if I had to consider all possibilities. Also, computers were becoming available. It was occasionally possible to get time on a mainframe, and so on and so forth. So people became to be interested in possibly solving these sorts of things. You know, whether this discrete optimization problem, which is in some sense our first instance of submodular function minimization from a historical perspective, could be solved in polynomial time. Now, given the first lecture of this class, you know that this is a polynomial time solvable problem. In fact, this could be solved fairly efficiently. But let's first of all prove this theorem. So the first thing to note, so what we want to do is prove, so let's go back to the theorem. Okay, so here's the theorem. Everybody look at it again. We're going to prove the first part, and we're going to say, suppose that V does have a system of representatives such that equation 6.5 is true. Equation 6.5, again, is that f of V of j is greater than or equal to the cardinality of j for all j less than or equal to I. Now, we know that f is monotone, right? And given that it's a system of representatives, we know that V of j is going to be a superset of the representatives, right? Because every representative is a member of its group, and so if we take the union of all of the groups, even if it's the case that the group only contains one member, if we take the union of the groups, that's going to be a bigger set than the set of representatives, right? So then what we get is equation 6.6, which is f of V of j being greater than or equal to that. Oops. You probably guys don't remember these things, so let's just go back to this theorem. So the point is that we know that this set here is going to be, this inner set is a subset or equal to the V of j, right? And so we already have this thing, and then we've got that this, since thanks to the monotonicity of f, we've got that this is greater than or equal to that, because it's a bigger set. Because V of j is a superset of the union of I in j of V of I. Hopefully that answers the question. That's the easy part of the proof. Is everybody clear on that? Because if you're not clear on that, the hard part of the proof is not going to make any sense. So I'll say it again just in case. So the green bit is greater than the yellow bit. We're assuming equation 6.5, and clearly the green bit is greater than the yellow bit because of the superset problem. Okay, I'm going to push forward now. Okay, so here's the converse. Actually, what we want to do first of all is the converse is actually easy once we've got this contraction lemma. So let's prove this contraction lemma. So basically it's saying that we've got equation 6.6, and it's restated here for you, for your enlightenment. And suppose this is true for this particular set of sets. And let's suppose, for the sake of argument, that there exists an I such that capital V of I is greater than or equal to 2. Right? So in fact, if all of the V's were equal to 1, right, then it would be clearly true, right? Because basically we get V of capital J is equal to the union of the V of I's for all J. Right? So it would be clearly true. The thing that gets tricky is when, so that would, for example, correspond to a bipartite graph where there's only sort of like horizontal edges. So that's trivial. So the only case that's not trivial is when there's some set V of I whose size is greater than or equal to 2, and let's assume it, and let's without loss of generality assume that it has index 1, because we can always reorder these sets. So then what we're going to do is prove that basically that if we remove, that there exists some V bar, which is a member of V1, such that we can also satisfy equation 6.6 by removing V bar from V1. Okay, so the way we do that is the following. So first of all, when equation 6.6 holds, so again, V1, we know that V1 has size at least 2, but we're not using that for this particular thing. Basically, if we take any two subsets of I that don't have 1 in it, then thanks to 6.6, we have f of V of J union 1 is greater than or equal to the size of J union 1. And that just basically is just a restatement of equation 6.6. And therefore, just simplifying this a little bit, we get this for J1 and this for J2. The right-hand side is trivial. It's just basically adding 1 to the size of J. And the left-hand side basically comes about just by the definition of the function V. Okay. So everybody got that? So now what we're going to do, suppose to the contrary, that there doesn't exist a V such that the family subsets also satisfy. So we're going to assume that this consequent is false. This is the consequent that I just highlighted in yellow. Then what we're going to do, that basically means that we can take any two elements, any two distinct elements from V1 and get something that's going to lead us to a contradiction. So we're going to take two distinct elements from V1. And so since it's false, it no longer satisfies equation 6.6. It basically means that when we've removed that element from V1, we're going to get an inequality the other direction, namely that the left-hand side is less than the right-hand side. And also when we remove V2 from V1, we're going to get the same thing, except for J2. And we're not necessarily saying that the J's have to be non-empty, but that doesn't matter. J's might or might not be empty. Okay. Now what we're going to do is we're going to rename these guys. So here, let's do this in color. Color makes this so much easier. So we're going to rename this guy to be X. I'm going to rename this guy down here to be Y. Okay. It's just renaming, and that's here what we're doing here. So we're renaming this guy to be Y and this guy to be X. Okay. So then, what do we have? Well, first of all, we know that we have f of x, that basically from looking at these two equations, we have that f of x is less than or equal to the size of j, and f of y is less than or equal to the size of j, the size of j1. Let me say this again. So f of x is equal to this, and f of y is equal to that. And f of x is therefore less than or equal to the size of j1, and f of y is less than or equal to the size of j2, which is this statement here. Now if we take the union of x and y, just by looking at it, set theory, we get that this is equal to v1 union v of the union of the indices. And if we take the intersection of x and y, we get that that is no less than v of the intersection of the indices. And I think we're missing an equation here, but what this is supposed to say is that when we look at, we've got, let me just write it here, J1 plus J2, the size of J1 plus J2 is greater than or equal to f of x plus f of y, which, thanks to submodularity, is greater than or equal to the f of x union y plus f of x intersect y. That equation seems to have scrolled off the bottom of the page. I don't know why, but in any event, there we go. And once we've got that, we can sort of put these two pieces together. We take the left-hand side here, and the right-hand side here, but now put back in the definitions of the union and intersection in equation 6.13 and 6.14, and we get the following. So we've used submodularity, that's all we've used. And of course we've also used equation 6.6. Right, for getting these guys. Actually we've used submodularity, which we know to be true, and we've used a consequence of the assuming to the contrary, which is equation 6.11 and 6.12. Okay. And we're going to lead us to a contradiction. Okay, so now we're getting back to the subsets V. We haven't removed an element yet. And so V, the original subsets, does satisfy equation 6.6. And notice that J1 and J2 were chosen both to not contain element 1. Okay, so that basically means that using equation 6.6 again, which if you'll recall is exactly that, means that this guy here is greater than or equal to this, which includes the 1, and this guy is greater than or equal to this, which doesn't. Now what do you think about this equation? Is that possible? We've represented everything in terms of cardinality. Cardinality we know to be a modular function. And so that's a contradiction of the modularity of the cardinality function. Therefore, our assumption to the contrary, that there doesn't exist a system of representatives once we've removed V bar from V1, must be false. So, this assumption, the assumption that there doesn't exist a family of subsets that also satisfies equation 6.6, that assumption that there doesn't exist must be false. Therefore, there must exist a V bar, that when we remove from V1, that guy still satisfies. So now, armed with that, basically, proving this theorem becomes very, very easy. Because basically what we're going to do, remember we're assuming 6.6 and we want to show that there's a system of representatives where 6.5 is. What we're going to do is start pruning off elements from V until basically we're going to have essentially a set of elements left, which is going to correspond precisely to this equation. Namely, we're only going to have one set of elements left. So basically what we do is we suppose that equation 6.6 is true, and if each of the VI's is a singleton set, then the result immediately follows. Why? Because that means that if every of the VI's is a singleton set, then that basically means that this green stuff here is the same as this. That's just the definition of V of J when all of the sets are singletons, right? So in that case, it's trivially true. And without loss of generality again, we're going to, let's say that V1 is the one that has not a singleton set, then when we use lemma 6.4.5, we can remove it. We also satisfy 6.6, and maybe at that point this becomes singleton set and it's trivially true, or if not, we just keep continuing to remove an element from any of the sets that have more than one element until we actually have all of them be singletons, in which case we've recovered essentially a subset of items which satisfies equation 6.5. Namely this one, this equation, 6.5. And the theorem is proven. And that will be a system of representatives, and again, for the right submodular function, if you use like the cardinality set, then it's going to have to be distinct. Yeah.
Would it be satisfied with equality then?
It will be satisfied with equality in that case because it's the same, because V of J is in that case is equal to this union of all of these. it's not necessarily satisfying the inequality with equality because it's a Polymatroid function, right? If you were, for example, to take the cardinality function, then it would satisfy it with equality. But a Polymatroid function, it would have to be independent in the matroid if it's a matroid rank function, and it would have to satisfy that inequality in the general Polymatroid case. So we've proven a very powerful and general theorem, and one that I think sort of really, begins to sort of help us to understand submodular function minimization and matroids and transversals. Now it turns out that a transversal is, some of you hinted at before, in fact, do themselves define a matroid. And so if V is a finite family of sets, then if you take the set of partial transversals and include the actual transversals themselves, that actually defines the independent sets of a matroid. So the transversals are the basis of a matroid. And so therefore maximal partial transversals, all of them have the same cardinality because it's a matroid. So all maximally independent sets of the same size in any matroid. And it turns out that we saw that in the partition, remember in the partition matroid, we saw that the partition matroid corresponded to matchings in a bipartite graph. This also corresponds to matchings in a bipartite graph as well, but it's a more general bipartite graph. In the partition matroid case, the bipartite graph itself consisted of multiple connected components. Namely, the number of connected components in the bipartite graph corresponded precisely to the number of blocks in the partition of a partition matroid. Here, you don't need that. So let's say that we've got, again, a set system, and we're defining an analogous bipartite graph, which has the same edge set, except that it's not restricted. And we have a matching in a bipartite graph. Does everybody remember what a matching is in a bipartite graph? Remember, in any matching, it doesn't have to be a maximal matching, but a maximal matching is a matching. It just happens to be one that's maximal. But in any matching, we're guaranteed that the edges incident to any node in the matching have cardinality 1 or 0. If it's a maximal matching, it also could be 0. But the point is that in a maximal matching, if you add any additional edge, it's no longer a matching. And so we easily have the following theorem, which says that if you have, in the bipartite representation of this transversal, you have that T is a partial transversal if and only if there's a matching in the bipartite graph in which every edge has one endpoint in T. So in other words, if T is a set of nodes and it has a matching where all T is covered. And in such case, we say that T is matched into I. So maybe I should have done this thing. So here's a. Do I have another picture here? No, I don't have the picture of this case. I thought I had a picture somewhere. Maybe I should have put this earlier. I don't have it. I was sure that I had a picture. But actually, if you go back to the, if you go back a little bit earlier, no, I do have a picture. It's a bit earlier. Give me 1 second. Searching for the picture. There it is. So if you go back to this picture, so it's a bipartite graph. And basically, it's saying that if we take any subset of the left nodes, like for example, if we take, let's take this one, or maybe this one, and this one. Could that be a partial transversal? Yes, because we could choose this edge, this edge, this edge. What about this? Could this be a partial transversal if we took this node, this node, this node? Could that be a partial transversal? No, because those three vertices can't be part of a matching that involves all three of those vertices. So if you take this edge, that basically means that we can't take this edge because that would mean that there's two edges incident to this vertex here. So therefore the yellow nodes that I've highlighted on the left can't be a transversal. And in fact, remember here that we gave a transversal. The transversal we gave was this one, and any subset of these ones that are currently marked corresponds to a transversal. And we can immediately, in this particular case, identify a matching. And the matching would correspond exactly to the labeling, the group that it represents. So that's the matching. And of course, any subset of the labeled nodes on the left also corresponds to a matching, because any subset of a matching is a matching. Matchings are down closed. So any questions? Okay, here's a question for you. Are arbitrary matchings matroids? That basically means that matchings are matroids. So transversal matroids are matchings. So all matchings in bipartite graphs are matroids. Are arbitrary matchings matroids? Because you can talk about other graphs, right? Other graphs have matchings, right? They don't have, it's not necessarily a bipartite graph. Do other matchings have, are matchings in other graphs matroids? Well, a spanning tree is not necessarily a matching. So what is a matching? A matching basically is essentially a set of edges such that no vertex is incident to more than one edge. So if we took, for example, this particular graph, on the left we have a graph. It's not a bipartite graph necessarily. We have two matchings, the one in the middle, which is red, and the one on the right, which is two edges.
Why is the middle one called max matching?
Sorry?
The middle one is a max matching?
Yeah, why is the middle one a maximal matching? So if I added any edge to the middle one, would that still be a matching? Let's try adding an edge, see what happens. So if I add that edge, is it still a matching? No. If I add this edge, is it matching? No. Aren't that many choices here? We can enumerate all of them. Are there any edges that we can add that retain matching? No. So this single edge is a max matching. What about on the right-hand side? Is the right-hand side a matching? Yes. Every vertex is, first of all, it's a max matching. It's a maximum matching. All vertices are matched, and every vertex is incident to only one edge. But if we add any edge, is it still a matching? No, because if we add this edge, or if we add this edge, or if we add this edge, it's no longer a matching. However, we've got two maximal matchings which are different size. So therefore, matchings in general graphs are not matroids, but matchings in bipartite graphs are matroids, are transversals in fact. So when you want to remember a transversal, what is a transversal matroid? It's very easy. Just think of it as the matchings in a bipartite graph. Which then generalizes the partition matroid, because in the partition matroid it's a particular type of bipartite graph, namely one where you have multiple connected components. In fact, here's the partition matroid. So what we want to do next, actually maybe we should take a short break. Let's take a short break, and then what we're going to do is we're going to morph from, I don't know if this is elucidating or not, but we're going to morph from the partition matroid rank function to the transversal rank function. Transversal matroid rank function. Okay, so the next thing we're going to do is sort of morph from the partition matroid rank to the transversal matroid rank. So let's start off with just a little bit of notation. So basically, remember in the partition matroid rank function, we have this bipartite graph representation where the k's, like ki corresponds to the size of the corresponding set. So here are the corresponding index set, that is. And so here are the set of index sets, I1, I2, I3, I4, and I5. And I sub 3 is the same, is the size of I3 is equal to K3. And that's basically saying this right here. And then we're also able, without loss of generality, to just assume that the size of the corresponding block is greater than or equal to the limit. Because if the size is less than the limit, then it sort of becomes a free block. That block becomes free. We can keep adding items up to that block. And then obviously, since it's a partition, we're not going to be able to add any more items into the block than there are items in the block to begin with. So without loss of generality, we can put this upper bound on K. Similarly to putting an upper bound on, like if you take the min of a function and a constant where the constant is greater than the min, you're not changing the function at all. Right? And I can also remember this. So I'm going to go through this a little bit quickly. Some of these steps are pretty easy to see. So here's the partition matroid rank function. And here what we're doing is we're just writing it in terms of I, right? The i's. And here what we're doing is we're just basically writing it as an optimization problem. So we're writing this minimization as an optimization problem. We're optimizing over all ji less than ii. And basically you can see that what this is going to do is if ji is equal to ii, in which case this part over here becomes 0, right? Then we're just going to get back this, which is going to be the left-hand side. And if ji is equal to the empty set, we're just going to get this over here, right? And that's going to be that plus that, which is going to be bigger than the min. And then the way that we can actually get this other thing is if I is equal to the empty set, right? So, and then basically what we're going to do is just get back the cardinality of this, okay? Now, the next step is actually also possible to show, but what I want to do is I'm going to leave this for a problem set rather than going through. So let's say that this equality is an exercise. So we've turned basically this minimization problem into an optimization problem over subsets. Okay. And now what we're doing is we're going to just write this subset out a little bit more in more detail, where we're taking I except for j. So we can actually just write this out since it's a modular function here. Okay. But now what we can do is actually we can switch the order of the summations and the subset optimization, where rather than within each I optimizing ji over I, we're optimizing all j, all the index sets over I. And the reason for that is because of the fact that this is a partition, and also moreover, this guy, v sub ii, partitions the left-hand side of vertices as well. And with a little bit of further simplification, we can show that it's equal to this, which then, once we've done it in this form, basically this becomes everything on the left-hand side, and so we write it in this form here. And that, it turns out, is exactly equal to the rank function of a transversal matroid. So what we've done is sort of, like when you look at the rank function of transversal matroid, you see this, and you might think, what does this have to do with the rank function of a partition matroid? And given they're so related to each other, that's a very sort of step-by-step way of going from one rank function to the other rank function. Now, on the other hand, it's not possible to go back because, again, the assumptions that we've been using to go from the partition matroid rank function to the transversal matroid rank function involved these independence, these non-intersecting properties, namely that it's a partition. But on the other hand, it's possible to show that equation 6.5 is in fact a rank function of a transversal matroid. So I guess as an exercise, I'd like you to sort of look over these steps and justify each one. Okay, but here's the actual proof. This is the thing that's going to occupy a bit more than I wanted to get to. So basically, we've got a subset system, a set system, V and script V, and I is an index set, and I is a set of partial transversals of V, and then the theorem is that it's in fact a matroid, so we want to prove this formally. So the first thing to note to prove it's a matroid is that the empty set is a member of the independent set. So the independent sets are the partial transversals. So is an empty set a partial transversal? It certainly doesn't violate any of the transversal properties, so therefore I1 prime holds. And then secondly, we've already saw that if you've got a transversal, then a subset of transversal is a transversal. So we've got the down-closed property of a transversal. Okay? Now this is the hard part. We want to show that if T2 T1 and T2 are partial transversals such that one is bigger than the other, then there exists an element in the larger one that can be added to the smaller one that keeps it a transversal. Okay. Actually, I thought I was going to show this, but actually it's the next theorem that we're going to prove, not this one. So this one is actually an exercise. Things, if I proved every theorem in class, we wouldn't have time for anything else. We have to push through these a little bit more. But these are good exercises. So if you finish homework 1 and you want to get onto homework 2, just look at the slides. Okay, because these are the homework problems. So here's the transversal rank function that we've already seen, and in fact is a submodular function, because we know that all rank functions are submodular. But what's interesting about this function is that this is the minimum over a set of what? For each j, what kind of function is it? Like if we fix j, rather than taking the minimum over it, just say that, suppose that j is a constant. What kind of function is this? It's a modular function. So remember before when we defined the matroid rank function, we said a max of this set of modular functions was a matroid rank function. Here now what we're doing is we're saying a minimum over a set of modular functions is a matroid rank function, and both of them are submodular. So part of what you're going to be doing, I think, on this homework is looking at instances of where minimum or maximum over modular functions preserves or doesn't preserve submodularity. In this particular case, it does. But here I'm leaving this as an exercise. Okay, are there any questions? Because what I want to do, we're going to talk about next is dual matroids, which I think you'll find very interesting, and matroid representation. But any questions so far on transversals? Okay, let's move on. A couple of more properties of matroids. These are things that we could have actually defined last lecture, but I'm defining them here because we're going to need them soon. So first of all, we know what the definition of a circuit is, right? And there's no reason that a circuit couldn't consist of a single element. Like, what would a single element circuit be? A single element has to be the case that its rank is less than its size. So what would be the rank of a single element circuit? 0. So what is there a vector? So I mean, so a single element is sometimes called a loop. So what would be the vector? What would be the vector corresponding to a loop or a single element circuit? A self loop in a graph, or if it was a vector in a matrix. Yeah, it's all 0. So the vector of all zeros has rank 0. It's still an index. It's still a vector. It still counts as one vector, but it has rank 0. If you add it to a set of vectors, you don't increase this. You don't increase the span, right? So in a linear matroid, such a loop is 0. If it's a graphic matroid, so you have a node, and the edge is a self-loop. Right? It doesn't help you to span the graph, in the sense it doesn't help you to, say, for example, have any additional nodes that are incidents instead of edges you're having. Now, here's another question for you. So, like, we saw that a graphic matroid and a matrix matroid are the same. Like, every single vertex in the graph could have a self-loop, right? So we could have lots of different loops in a graph, lots of different single element circuits. But how many different loops are there in a matrix? There's one, which is the all-zero vector. So how is it the case that there can be more loops in a graph than there can be in a matrix, given that they're isomorphous to each other? Well, it turns out that in some sense they're indistinguishable. You can always have more than one vector that's all zeros. You can also have more than one loop. You could have 2 loops here, incident to the same node. Or is there any way of distinguishing those 2 loops from, say, these 2 loops? No, they behave exactly the same. So it doesn't really matter what vertex a loop is incident to. You could stick all of the loops and add them onto one vertex. You could have a whole bunch of loops there if you wanted to have loops in your graphic matroid. So the other thing we say is that if 2 elements themselves form a circuit, then we say that they're parallel. And this corresponds to like parallel edges in a graph. This would be a non-simple graph. Okay, so with regard to like matroids and representations, a lot of what the theoretical work on matroids is trying to see what matroids are identical to another matroid. And we need a notion of what identical is. And so there's this notion of matroid isomorphism. And so 2 matroids are said to be isomorphic on 2 different ground sets if there's a bijection between the ground sets that preserve all of the properties of the matroid, namely the rank functions or the circuits or the bases or any of the things that define a matroid. And so if you can map from one to the other and you preserve all of that for all particular possible subsets, so you preserve the independent sets, for example, then the matrices are the same. So if, for example, I could take any matrix, like I could take any graph, and I know that, for example, any graph can be represented with a matrix. And so the kinds of questions, and this is a very rich field, the kind of questions people ask, and this is primarily studied in the mathematics community, kind of questions is like, for example, what subclasses of matroids are identical to each other? So like, for example, you can set F be any field. And field could be like the real numbers, or the rational numbers, or any field like a Galois field, like GF2, which is like the binary numbers, with binary modular 2 arithmetic. And you could define a matrix on a field. And the question is, for example, by restricting the field within which the matrix is defined, does that somehow restrict the matroid that's resultant? Like the matrices that we've been defining use the reals, the real fields. But what if we use GF2? Like, can that represent anything? And there's also something else in a matrix. There's the dimensionality of the vectors, whether or not you can do this with bounded dimensional or infinite dimensional vectors. And so more generally, we can define matroids on a field. Like we have this matrix, which is an n by n matrix. We have a ground set which consists of the m column vectors, or the indices of the m column vectors. Each element of the matrix is a member of the field. And we define the independent sets, which are subsets of the column vectors that are linearly independent in F, where using field arithmetic, we're linearly independent. Namely, for example, it's impossible to take a linear combination of any subset of vectors to get any remaining vectors. That would be independent. Same definition, except it's using a field. And so there's this notion of representable. And in some sense, since matroids, in some sense, I guess you could say, going back to Whitney's paper, came from abstract properties of matrices, of column spaces of matrices, the notion of representableness corresponds to whether or not a particular matroid that you defined is possible to have a representation as a matrix in some field. So in other words, take one of these transversals I've got, or take any matroid you can imagine, where all we're using to define the matroid is the definition of the matroid. Namely, it's empty set containing, down, closed, and satisfies one of these exchange properties. We use that as the definition. We define some algebraic property that satisfies these definitions. Is it necessarily the case that there is some matrix over some field where the vectors are of some dimension that can represent that matroid? And that's the notion, that's the question of representability. So just intuitively, what do you think? So is it possible, so we've generalized the abstract notions of matrices to matroids. Can all matroids be represented by a matrix? are all matroids representable by some field, possibly an infinite dimensional space? Raise your hand if you think all matroids are representable. Okay, so raise your hand if you think that there are matroids that are not representable. Raise your hand if you just read an extremely funny post on Facebook. One of you did, I didn't. The ones of you who are not smiling, the non-smiling people in this class have just read something very funny. Right? The smiling people are engaged. So, why do you, for those of you who thought that all matroids are not representable, why do you think so? This is a really interesting thing. I mean, it's really, like, first of all, it would be very disappointing. You could use it based on prior sort of cultural knowledge of the mathematics community, which is that if it's the case that basically what Whitney did is to find something which is exactly a matrix, maybe matroids wouldn't be that interesting. So you might say, well, why would there be such a fuss over matroids if it's the case that they're just matrices? So you could have a prior bias on that. But on the other hand, maybe you have some other reason to think that not all matroids are representable. Well, think about that. So there have been theorems, like for example, even transversal matroids. There was an important theorem proven about them, the ones that we just studied, namely that transversal matroids, as rich and flexible and perhaps thought by some amazing as they are, that they're representable over all finite fields of sufficiently large cardinality, and are represented over any infinite field. So that basically means that transversals, you're not really leaving the space of matrices. So what do you think now? Do you think that all matroids are representable? So transversals are representable. Converse is not true. So here's for example, this is it's a very small matroid. It's ground set of size 6. And let's say that the independent sets are all subsets of cardinality 2 except for the pairs 1, 2, 3, 4, and 5, 6. Okay. So this is a matroid and it's representable. So there's a matrix corresponding to this. However, it's not isomorphic to any transversal matroid. So there's no transversal that can actually represent this matroid. Okay, we're gonna visit this topic again next lecture, the notion of representability, because what we're going to see, and I'm going to give you some examples. I don't think I have them here, but we're going to see some examples where you have matroid. I'm not ending the lecture yet. I'm going to go for about another 5 minutes because I want to define a dual matroid before we reach Monday's lecture. But what we're going to see is that there are matroids that aren't representable at all. They're very, very strange matroids. But what we need to do, and we won't get that until Monday, we need to sort of understand a little bit more about how matroids correspond to sort of abstract geometries. And we'll get into that on Monday. In the meantime, let's just sort of briefly talk about a dual matroid. Because a dual matroid is absolutely, I think it's an amazing construct. And when you look at, for example, like a dual graphic matroid, or what's called a cocycle matroid, you get into some very, very interesting constructs. So just as a reminder to everybody, so what is closed flat or subspace? So basically a flat of a matroid is one such that if you add any additional elements, a flat of a set is a construct such that if you add any additional elements, you necessarily must increase the rank. So you're sort of maximally inclusive without increasing rank. And then the closure of a set is basically adding items that don't increase the rank. So it's a closure property, and then there's the circuit, which is inclusion-wise minimally dependent. We have additional definitions that we need. We need the notion of a spanning set. A spanning set is one whose rank is equal to, let's just read it. So if you got some matroid, and if you get some set Y, that any subset of Y is a spanning set of Y if it's got the same rank. Okay, so a spanning set of a matroid then is going to be a subset that has the same rank as the matroid. So why is it spanning? Because again, when you think about the notion of a matrix, any subset of vectors that's spanning spans the entire column space of the matrix. So it's a spanning set of vectors. But whenever you have a graphic matroid, a spanning set, a spanning set is any set that contains a spanning tree. So a spanning tree is a spanning set that happens to be a tree. And that's why it's called a spanning tree. Has anyone ever wondered why it's called a spanning tree? Those of you who've done undergraduate computer science classes before? It's because of that. It's because essentially it corresponds to this matroid property. I dare you to ask that question of any undergraduate algorithms teacher who's explaining to you concepts of spanning trees. But now you know. Okay, so the base of the matroid then, therefore, is a spanning set, and it's a minimally spanning set, and if it's the case that it's a graphic matroid, it's a spanning tree. The ground set is always spanning, but there could be other spanning sets. Any superset of a spanning tree is a spanning set, or any superset of a base in a matroid is a spanning set. So once you've got a base, you can keep adding things, you're not increasing the rank, but you still have the rank, and so therefore you're spanning. And so that's right. So this is the spanning tree in a graph. So let's just define a dual matroid, and then we can finish for today. Because it's really, really interesting. And so next time what we're going to do is go over the proof of why it's still a matroid. But let's say that we've got some matroid, and we're going to define a dual of a matroid, M star. And the dual of the dual is equal to the matroid. So it's basically, it has that property. So we've got a set of independent sets of the matroid, I, here. And we're defining the dual of the matroid as that matroid that has as independent sets I, such that I's complement is spanning in the original matroid. So if you are a set, and the complement of the set is spanning in the original matroid, then you're independent in the dual matroid. So if you're a set, right? If you're one, let's think about it in terms of a graphic matroid. If you choose one edge, right, in the graphic matroid, and then you take the complement of that edge, which is basically everything but that one edge. So that's going to include a spanning tree probably, but it won't have that one edge. But it'll have everything except for that edge will include a spanning tree and a bunch of other stuff, right? So that one single edge is independent in the dual matroid, because its complement is spanning in the original matroid. What if we take, for example, something that removes everything but a spanning tree? Okay, so let's say take the original matroid, and you take a spanning tree, and take its complement. Okay, so it can have cycles, and it can have all sorts of stuff, and it can have lots and lots of cycles. Its complement is a spanning tree. Okay. So then, if you take the complement, we still get a spanning tree, so it becomes independent in the dual matroid. So it's totally strange, but it's true. So a set is independent in the dual if its complement is spanning in M. So another way of thinking about it in words is that the residual must contain a base. So V minus I must contain a base in M for I to be independent in M star. So in the cycle matroid, any spanning set of G is any set of edges that are incident to all nodes, right? Remember that. Now there's this dual thing associated with the bases. So let's say you take the smallest spanning set in M are bases in M, right? Those are the span, like if it's a cycle matroid, it's a spanning tree, right? And, right? And those are complements of the bases in M prime. So let's think about it this way. So you've got a base, base in M, okay? Then if we've got a base in M and we remove it, so the base in M is like, it's a spanning set, right? And so if we remove everything but that guy, right, that's going to be a base in M star. So there's this dual nature. Okay, so we're going to actually prove this next time, but we're running out of time. But are there any questions about this? Yeah.
The ground set is same for both M and M star, right?
Yes, the ground set is the same.
And if we say that script I is the set of all independent sets, subsets in M, that means the complement of I will be the set which contains non-independent sets, right? If I is the set of all independent subsets, then the complement of I will contain elements which are no longer independent.
Okay, maybe you know what I maybe should have done. This notation is a little bit confusing possibly, but what if I define it as this? If I just say A is less than 3 such that A, this is spanning. So we're not necessarily saying that we're only defining the independent sets of the dual matroid by saying that the complements of the sets have to be spanning in the original matroid. So, and that defines I star. So let's call this A instead of I. Because I usually, we've been using I for independent sets in the original matroid, and maybe we're using I star for independent sets in the dual matroid. So let's think of this as A rather than I. And you're right, absolutely right, I should have written this too. So this is the definition of the matroid.
Then I have another question.
Yep.
The complement of a spanning tree cannot be a spanning tree, right? Okay.
So if you've got a spanning tree, okay, and you've got its complement, it could still be spanning. It's probably not going to be a spanning tree. I mean, it might be a spanning tree. What if you have this, a very simple set of parallel guys? So this is a spanning tree, which is one edge, and the complement is another spanning tree, which is another edge. So the complement of a spanning tree can be a spanning tree.
But not necessarily.
Not necessarily.
But in our definitions, we have been defining that the I star or I is the set of all independent sets. So sort of the spanning tree comes out of I, right? And if we are saying that V minus A is the spanning set of M, that means the complement which we are taking, calling it I star, also has to be a spanning tree itself. Within it can be.
No, the complement has to be independent. These are I star is the independent sets. I star is not necessarily the spanning sets. It's only the maximal members in I star which are going to be spanning in M star. But we're defining the independent sets in M star, which are not necessarily spanning, as being those guys whose complements are spanning in M. It's very strange. You have to think about this, but as we will see on Monday, there are some examples that show you that you can get some very, very crazy looking independent sets in a graph by looking at the dual matroid.
So is the dual matroid generally a matroid?
Yeah, we have this theorem, which we're going to prove next time. It's always a matroid. I personally think, just why I think this relates to machine learning is I have this belief that the dual matroid of even a graph is something that has been completely underutilized as potential to be something useful in machine learning applications. For example, when you get into constraint submodular optimization for various different applications, the algorithms are basically defined to be based on constraints that can be any matroid, which could be the dual matroid of some graph. Dual matroids are also nice because it's easy to check independence. We need sort of computationally viable matroids, and what's nice about graphic matroids and dual matroids of graphic matroids is that rank functions and independence queries are relatively easy. You don't need, for example, when you're actually implementing this, to actually have a long, exponentially large list of the independent sets. You can just have the graph and then just do a little bit of operations on the graph to query whether or not a particular set is independent. So that's another reason why we're spending time on this. So, the slides are online. I suggest everybody read them before Monday. One last thing on the homework. Don't wait. This is a long homework. I promise you this is a long homework. I would really like everybody to spend time on it, okay? Spend real time on it. So start the homework now. Okay, I've given you 8 days. You can definitely do it if you start now. You cannot do it if you start Tuesday night. Okay. All right, I will see you on Monday.